Okay, so welcome back, everyone. Thanks for being around. We have our second talk of this probability session regarding the 60th anniversary of Simvestab, and in particular of the Department of Mathematics. So for this session, we have the pleasure to introduce Professor David Nualart. He is the Black Babcock Distinguished Professor in Kansas University. And Professor Nualart, he did his PhD in the University of Barcelona. He is very well known for all his work in the so-called Malliavin calculus. He has a book called actually the Malliavin calculus and related topics. He's very well known because of that, and he has more than 22 PhD students. And for you to know something brief, he's been elected fellow of the Institute Mathematical Statistics. And something also very interesting is that he's got a doctor honoris causa from the University of Blaise Pascal in Clermont-Ferrand in France, right? So he's going to talk this morning or today. He's going to give this presentation about the spatial ergodicity and central limit theorems for the stochastic heat equation. So please, David, thank you very much. You can start.
Thank you. Thank you very much for the presentation. It's a pleasure to give this talk here in the celebration of the 60th birthday of the Department of Mathematics in the Simvestab. As I was saying, the Simvestab was the first mathematical center. The Department of Mathematics was the first center I visited in Mexico a long time ago to work with Luis Gorostiza. And since then, I visited other universities in Mexico. So what I'm going to talk about today is a topic that has been developed in the last more or less 3 years. And it's a joint work with several people. I named some of them here in the first page. Xingyu Wang, Laura Vitasari, Lei Chen, Davarko Shinavisan, Fei Pu, and Wang Chuzhe. And actually the first work started with the first two authors, Wang and Vitasari. And this is about properties of the solutions to the stochastic heat equation in the space variable. So we are interested in ergodicity and central limit theorems, but the variable is not time as usual, but the space. Remember, stochastic PD, the solution is a random field. There are two parameters, time and space. And here we will be interested in the space as a parameter. Okay, so I will formulate the equation and the main results, and we'll try to give you an idea of the methods that we have developed to prove ergodicity and solve central limit theorems. Okay, so let me see if I can pass the page. Okay, so here is the equation. So this is the heat equation on RT, partial U respect to T equals to 1/2. Well, this is the probabilistic heat equation because this is the 1/2. The analysis heat equation doesn't have the 1/2, okay? This is because we want the fundamental solution to be the heat kernel. And so we are probability people, so we put the 1/2 here. Okay, and then we have a forcing term, which consists on nonlinearity function of U times the noise, W dot. And I'm going to choose the initial condition, which is a flat. That's very important because we are interested in stationarity. So the initial condition is 1. Okay, so what is the noise? The noise W dot is a random field, depends on T and X. It's a Gaussian. And the covariance is a Dirac function in time, so this is heuristic, and some gamma function in the space. So the important thing is that the noise is white in time. That's very important because this will allow us to use martingale methods to deal with the solution to these equations. So the noise must be white in time. And in a space, you can put a white noise if you want, but you can allow a more general homogeneous covariance given by gamma, where gamma is a non-negative function or even a measure. And then the condition that people impose to gamma for this equation to be a solution is that the Fourier transform of gamma that I denote by mu, which is the spectral measure, satisfies this condition. It integrates 1 over chi squared. So this is almost a necessary condition in the sense that if sigma is constant, this condition is necessary. So it's really the condition that your covariance must satisfy to be able to solve the equation. Okay, and sigma is Lipschitz, and just sigma 1 different from 0 to avoid the trivial situation. Okay, so that's the equation, and let me give you a couple of examples of this spatial covariance. One is the risk kernel, which is x power minus beta, and then the Fourier transform is c to the power beta minus d with a constant, that's well known. And then you can easily check that this condition is satisfied if beta is less than 2. So you need beta less than 2 and beta less than the dimension, okay, for this to be integrable. So that's one of the basic examples that people have studied. And then the other example is the space-time white noise. So when the noise is white in time, so gamma is delta 0. And in that case, if gamma is delta 0, mu is the Lebesgue measure. And if mu is the Lebesgue measure, this interlevelity condition is only satisfied in dimension 1. In dimension higher than 1, it is no longer integrable, if mu is Lebesgue measure. So that's the reason for if you want to deal with the space-time white noise, you have to restrict yourself to dimension 1. Okay? So these are the two basic examples we are going to deal with. Okay, so to make things a little bit more formal, to define the noise, actually what you do is you consider the noise as a family depending on the test function phi, and then the covariance is given by this. So phi is a function of space and time, and you see the noise is white in time, so you have a ds here, and then in space you have this gamma of x minus y. Okay, and then because the Fourier transform of gamma is mu, this can be written in that way using the Fourier transform, where f is the Fourier transform in the space variable. So this defines an inner product that I denote in that way. And then what happens is that if you take the completion of test functions with respect to this norm, you have a Hilbert space, and then you have a Gaussian family of random variables. And that's the rigorous way to introduce the noise. So you introduce the noise by giving this Gaussian family of random variables parameterized by this Hilbert space in such a way that the covariance is exactly the L2 norm, the inner product in the Hilbert space. And this corresponds to the covariance. So what is W dot? Because remember that in the equation, there was a W dot. So the heuristic is that W dot is just the density of W with respect to the Lebesgue measure. So that's formal because W is not going to be smooth. But roughly, this W dot is the partial derivative of W with respect to time and space. Or in other words, if you want, this W of phi, heuristically, is the integral of phi with respect to W as a measure. Okay, you can put here W dot dx if you want. So this is purely formal, pure heuristic, sorry. And the formal definition is this one. And these covariance that I put here, like delta 0 times gamma for W dot in terms of W is exactly this formulation here. Okay. So that's the rigorous way to introduce the noise. Okay, so now you can define, we need the stochastic integrals. If you want to define a solution, you need to introduce stochastic integrals. And to do this, we introduce a sigma algebra, filtration FT if you want. So FT is the sigma algebra generated by the noise up to time t. So this is an increasing family of sigma algebras. Okay. So this means that you can define martingales, and you have an increasing family of sigma algebras here. And then you can consider adapted processes. So U is a random field, depending on time and space, and is adapted if UTX is FT measurable for all t. And then you can define a stochastic integral the stochastic integral of an adapted process, which is square integrable in the sense that the H norm has finite square expectation, and then you have this isometry property of the stochastic integral. So in some sense, the Ito theory of stochastic integration can be extended to this framework, and the only difference is that the isometry is obtained through this H norm of U, where the H is this Hilbert space associated to the covariance that we have introduced before. Okay, so you have a notion of a stochastic integration, and then you can define now my solution. So my solution will be this integral equation, the solution to this integral equation. So you have a 1 here, because remember that the initial condition is 1. Here you have the fundamental solution to the heat equation, which is given by the heat kernel. And then you have the sigma of u w ds dy. So this is a stochastic integral, this kind of extended Ito stochastic integral. And then this is an integral equation that you can try to solve using Picard iteration methods and usual techniques. And then this goes back to Robert Dalang in 1999. Well, actually, for space-time white noise, this theory was developed by John Walsh. John Walsh gave a wonderful lecture notes in '84. I was very lucky to attend these lectures. But this was mainly for essentially the space-time white noise case, when dimension is 1. And then this extension to an arbitrary gamma correlation was developed by Robert Dalang, and his main paper is a paper in 1999, and he proved that there is a unique solution which has bounded moments of all orders, okay? Bounded moments in space and in time in a finite interval. So this is a basic result, that you have this solution. So this is kind of introduction to this theory of stochastic heat equation. So what we're interested? So we fix time, and we are interested in the solution as a function of x, where x is the space. Then I claim that the solution is always stationary, and if the spectral measure doesn't charge 0, then is ergodic. So that's a condition for ergodicity. And to give a little bit of history about this, it turns out that this condition actually is necessary when sigma is constant. And this is related to a paper by Maruyama in '49, where he studied ergodicity for just one parameter Gaussian stationary processes. And necessary and sufficient for ergodicity was this, that the spectral measure doesn't charge the origin. So it's actually natural that we encounter here the same condition that Maruyama found for stationary Gaussian processes, one-dimensional one parameter stationary Gaussian processes. And it turns out that this condition is also sufficient in the nonlinear case. Okay, so this is a general result in the nonlinear case. So let me give you some ideas of how we can prove these two results, stationarity and ergodicity. So the stationarity, I will not give any technical details, just tell you that the stationarity is a consequence of the fact that we take initial condition, which is constant to 1, and then that the covariance is spatially homogeneous. And it's very easy to show that the solution is stationary. And not only this, but the solution UTX can be written as the composition of UT0 with a shifted noise. And the shifted noise means that you just, in the definition of the noise as an integral with respect to W, you just make a shift by X. So you define the shifted noise, which is a noise with the same covariance structure as the initial noise. And then you solve the equation with the shifted noise. And then the solution at time 0, at X equals to 0, coincides with the solution at value X with the original noise. And because of this, the stationarity follows immediately, because you have a composition with a shifted noise, and then because the covariance is homogeneous, you get the stationarity immediately. So that's the proof of stationarity. What about ergodicity? So the ergodicity, let me give you the main ideas. So first of all, because you have stationarity, you have the ergodic theorem. This means that if you take nice functions Gj, of the solution, evaluated at some points x plus theta j, and you integrate it in a space in some bounded interval, and you divide by n power t, then you can apply the ergodic theorem, and it tells you that this converges in L2 to the conditional expectation of this functional when x is 0 with respect to the invariant sigma field. So that's always true, and that's a consequence of the stationarity and this ergodic theorem. Now, ergodicity means that the invariant sigma algebra is trivial. And this invariant sigma algebra trivial means that this converges to a constant. So this means that the variance converges to 0. So to prove ergodicity, you just have to prove that the variance of this quantity converges to 0. Now you have to get a way to estimate these invariances and to prove that they tend to 0 as n tends to infinity. So that's the technique to prove ergodicity in this context. Okay, and how do you control this variance? Well, when I started working with this, Davar, Kushnevisen, and collaborators were also interested in this problem, and they have a very complicated way to compute the variance. And it turns out that this variance can be estimated easily using Malliavin calculus. Of course, if I am giving a talk, you can expect that there will be Malliavin calculus at some point. Okay, so the Malliavin calculus is the right tool to estimate this variance, and this is done through some inequalities called the Poincaré type inequalities. So let me make a brief introduction to Malliavin calculus and these Poincaré type inequalities to show how to prove this, that this variance tends to 0. So I make a parenthesis in my talk, and then I'm going to talk about Malliavin calculus in a couple of slides. So what is Malliavin calculus? So it's a differential calculus with respect to the noise. So you are going to take the derivative of random variables, and then you start with random variables, which are very nice, which are smooth and cylindrical. So there are nice functions of a finite number of Gaussian random variables, WH1, WHN, where HI is nice also. And then you define the derivative of a function of this type using chain rule. And then the idea is that the derivative of WHI is just HI. So in some sense, the derivative, so we remember that WH is the stochastic integral of H with respect to W. The derivative is the inverse operation of the stochastic integral. So when you take the derivative of WH, you get H at the point Sy. So the derivative is going to be a random field. So actually it takes values in H. And then you construct Sobolev spaces, call it D1P, which are the completion of this set of smooth random variables with respect to Sobolev norm, which is the LP norm of F plus the LP norm of the derivative with values in H. So this is Sobolev space. Okay. And another ingredient that we need is the divergence, which is the adjoint of the derivative, and is obtained through this duality formula. So here you have df inner product with u, where u is a random variable with values in H, equal to the expectation of f times some delta u. So if there is a delta u such that this is true for every f, then you say that u is the domain of the divergence. So this is the adjoint of an unbounded operator. Okay. And then a very important fact is that this divergence coincides with the stochastic integral if the random field u is adapted. So if v is adapted, so v is a random field is adapted, then v automatically is in the domain of the divergence, and delta of v coincides with the stochastic integral. So actually, this was discovered in the case of the Brownian motion by a couple of mathematicians, and later was with Etienne Pardue. We worked on this, and we developed a stochastic integration of anticipating processes using this divergence integral. Okay. So for Brownian motion, the same result is true, and this is actually an extension of the result for Brownian motion. Okay, so the summary is that you have a derivative operator, the adjoint is the divergence, and this adjoint, which acts on random fields, is an extension of the stochastic integral, in the sense that an adapted process automatically belongs to the domain of the divergence, and the divergence is equal to the stochastic integral. And actually, this property will play a fundamental role on what we are going to do later. Okay, so this is my short course on Malliavin calculus. I will not give you any more notation or definitions. And here is this Poincare inequality that we're going to use. So if you have two random variables which are differential in the sense of Malliavin calculus, the covariance can be estimated by this. So you take the derivative of f, the L2 norm, the derivative of g, the L2 norm, and you take the inner product with respect to the gamma. So you, multiply by gamma of y minus z dy dz ds. And this is the bound for the covariance. Okay. So you can estimate the covariance if you are able to estimate the L2 norm of the derivative of the random variables. That is essentially this Poincare inequality, which goes back to the idea of estimating the variance by the L2 norm of the derivative, which is the original Poincare inequality. But that's a version of Poincare inequality in this context. And this is proved as a consequence of this Clark-Occon formula, which is a stochastic integral representation of a random variable in terms of the derivative operator. So if you take a random variable f, so you know that for Brownian motion, any random variable can be written as a stochastic integral, expectation plus a stochastic integral. So here the same thing, when you have this more general noise, is true. Any random variable which is square integrable can be written as the expectation plus a stochastic integral. And if the random variable is differentiable, the integrand can be written using the projection on the sigma field fs of the Malliavin derivative dsy. And then once you have this, using the isometry property from this, it's very easy to get this. Because to get the covariance, you just use the isometry property, and then you take the L2 norm, the conditioning disappear, and then you get this. Okay, and this Clark-Occon formula is also an important result about the stochastic integral representation. Okay, so now we are ready to give you, I'm not giving you all the details, but some ideas of how to prove the ergodicity. So remember that we have to prove that this variance tends to 0 for some functions of the solution. Then the first idea is that there is a reduction. So you can replace this complicated function, which is a product of gj's of u, by just a function g, a random variable g, sorry, composed with the shifted noise. Because by stationarity, u is u of t0 composed with the noise. So you can replace all of these by just g of x, where this is g composed with the shifted noise. Okay. So in other words, you have to prove that this variance tends to 0. So I repeat, I'm going to replace all of these complicated random variable by just g of x, where g of x is g composed with the shifted noise, and g is smooth. So we have to prove that this variance tends to 0. Well, you develop the variance. So this is 1 over 2 power n, 1 over n power 2d, integral of 0n power 2d, covariance of gx prime. Now, Poincare inequality. You estimate the covariance by this. This is just Poincare inequality. And then the derivative of g, because g is smooth and is just a composition of g with a shifted noise, can be written, can be seen that you can make the shifted noise disappear, and you just shift the derivative. And this derivative is bounded by this, where c is a nice function. And this is because we have taken g, a very nice random variable. So in other words, without too many details, these two things are going to be bounded and compact support. So these disappear, compact support in y and z. So this disappear and this disappears. And then finally, you just have to take the integral of gamma on this square shifted by x. And then after some manipulation and using the Fourier transform, the gamma disappears. And instead of the gamma, you have the spectral measure. And then you have the Fourier transform of this indicator function. So finally, you get this Fourier transform square integrated with respect to mu. And then this is easy to compute. You get something like this. And then it turns out that as n tends to infinity, this converges to 0 always, except that c equals to 0. And then if mu of 0 is 0, by dominated convergence, you can prove that this converges to 0. So here is where this condition appears, because you have this c in the denominator. Okay. So I didn't give you all the details, but essentially the idea is that you have to prove ergodicity, you have to prove that some variance tends to 0, and then you use Poincare inequality, you estimate the variance by the Malliavin derivative, then you take, by an approximation argument, you can take a nice function, and then you use the fact that well, you have this spectral measure that doesn't charge the origin. So I'm not going to give more details because this is already too technical. And so now once you have proven that the solution is ergodic in X, then you want to try to prove a central limit theorem. So to do this, you take the solution UTX, you subtract the mean, which is 1, and then you integrate in the space variable and you divide by n power d. So this is the average. And of course, by the law of large numbers, this is going to converge to 0. And then you want to prove a central limit theorem. Okay. By the ergodic theorem, sorry, this is because you have ergodicity. By the ergodic theorem, this is going to converge to 0, and you want to prove the corresponding central limit theorem. So you see this converges to 0 in LP for all P by the ergodic theorem, and you want to prove the corresponding central limit theorem. And to do this, you need the asymptotics of the variance first to see what is going to be the rate at which this converges to a normal. And then here are the two results. There are two different cases. One is when gamma is a finite measure, so where gamma is integrable. And then in that case, the variance is of the order n power minus d times this constant. Okay. And in particular, in the case of the space-time white noise, this is the limit instead of this. Okay. And then the other case, interesting case, is the risk covariance. And then in that case, the rate of convergence of the variance is r power beta, where beta is this quantity here. Okay. And then the result is a little bit different. There is an interesting difference between this and this. Here you have the square of sigma and the expectation, and here you have the expectation of sigma and the square is outside. So it's really very different, this and this one here. Okay. And this had a constant here, which depends on beta. Okay, so these are the asymptotics of the variance. They can be obtained easily. It's not very complicated. And then this is the central limit theorem that I'm going to state here in a functional version. So as a process in time, okay, in time. And it turns out that as a process in time, if you take these spatial averages, multiply by n to the power d over 2, because this is the rate of the variance. And then assuming this first, then you have convergence in the space of continuous functions to a Gaussian martingale. So a Brownian motion with a time change if you want. And the variance is given by this deterministic function. So this is the case where gamma is a finite measure, which includes the space-time white noise. And then in the case of the risk kernel, then, oh, here there's a mistake. This should be beta over 2, not d over 2. It should be beta over 2, okay? So the rate is beta over 2 because you get the beta here. There should be beta over 2. And then the limit again is a Gaussian martingale. Okay, so I will not give you the proof of this, but instead of this, in the second part of my talk, I will explain another type of results that we have obtained, and this is called quantitative central limit theorems. So central limit theorem means convergence in distribution. So there are situations where you can get a strong convergence, stronger convergence, convergence in total variation, and you can get a rate of convergence in total variation. And this is a topic that has been developed in the last, I don't know, 15 years, using Stein's method and Malliavin calculus. And this has been developed mainly by Ivan Nourdin and Giovanni Peccati. And I would like to talk a little bit about this and how these results and these techniques are applied to our problem. So I'm going to change a little bit of topic. I'm going to introduce the total variation distance between two random variables, which is actually the total variation between the probability distributions. And then I'm going to state the basic result, which is this. So you take these spatial averages, you normalize to have variance 1. So you divide by the square root of the variance. Then this, by the central limit theorem, converges to the normal 0, 1. And then here, so here t is fixed, so it's not functional. So the result is that this converges in total variation distance to a normal 0, 1 random variable, okay, for t fixed. And not only this, but we get a rate of convergence. So the rate of convergence is n to the power minus beta over 2, where beta is, if the measure is finite, beta is d, and if not, you have the risk covariance, beta is the parameter of the risk covariance. So this includes both cases, the case of a finite measure or the case of a risk covariance. Okay, so this is the main result that we have obtained for this type of problems. You get a rate of convergence, and the rate of convergence is more or less natural because it's exactly related to the variance. So it's exactly what you can expect. And then in the rest of my talk, I'd like to tell you how to prove this type of results. Okay. So this goes back to the Stein's method for normal approximation. So now this is completely different stuff here. So I'm talking about Stein's method. So what is Stein's method? So first of all, let me give you this lemma, which is a characterization of normal 0-1 random variables. So random variable z, which has finite expectation, has normal 0-1 even only if for every test function phi, this expectation is 0. So this is the expectation of phi prime of z minus z phi of z. If this is 0 for any test function phi, z is normal 0-1. So that's an elementary probability result, okay? That you can give us an exercise in a basic probability course. Okay, so what is the Stein's method? So the idea is that suppose that you have a random variable f, which is not normal 0-1, but suppose that this quantity is small for a suitable class of functions. Then the distribution f is close to the standard normal. And the Stein's method, the idea is to quantify how close the distribution of f is to the normal distribution in terms, for example, of total variation distances, assuming that this is small. So we are going to estimate the total variation distance between f and a standard normal random variable by quantities of this type. So that's the idea. And how do you do this? Well, you take something called Stein's equation, which is a linear differential equation of this type. So here h is a given function. And then, so the right-hand side is given. And the left-hand side, you have an unknown function phi, and you want phi prime minus x phi equals to this. And the solution depends on h, of course. And the reason we take this quantity here is because this is related to this, you see. Okay. So this is what is called the Stein's equation, and it has a unique implicit solution of this form, which is obtained by just integrating this using Gaussian kernels, and is unique with some boundary conditions. And this solution is bounded, and it has a bounded derivative by 2. So that's a yes. Go ahead. Is there a question or?
No, I don't think so.
Okay, good. So this is what is called the Stein's equation, and it has a solution. And the only thing we need to know about the solution is that it's bounded and it has a bounded derivative. So now what you do is the following. So you can prove this result. So the total variation distance between a random variable f and a normal 0-1 random variable z is bounded by the supremum of these quantities, where phi is in the set of functions which are C1 and satisfy the same condition as the solution of the Stein equation. So you take all the functions that satisfy these two bounds, you take this expectation, and the supremum of this is a bound for this total variation distance. And the reason is very simple. So here is a very simple proof. You take the Stein equation, you replace x by f, you take the expectation. Of course, when you replace x by f, if you take the expectation, you get this. And here you get this. And then, of course, this is bounded by the supremum for all the functions that satisfy the condition that are satisfied by phi of h. And this is true for every h, which is a nice continuous function with value 0-1. And then you can replace h by an indicator function, by an approximation argument. And then the supremum with respect to h here gives you the total variation distance. So that's a very simple proof. And this is a very general result that, as I told you, this is just the Stein's method that it's, well, no, there's no Malliavin calculus yet here. So now, in order to estimate the total variation distance, you have to estimate this quantity here, okay? And there is no Malliavin calculus, so this is very general. How to estimate now this quantity, given a random variable f. And now here is where Stein meets Malliavin. So now you have this normal Gaussian process, and you have Malliavin calculus, and then you have this theorem that goes back to Nualart and Piccati, and it tells you the following. Suppose that you have a random variable which is normalized, so it has variance 1, it has 0 expectation, and f is the divergence of u. F is the divergence of u, for some u. Then the total variation distance between f and z is bounded by twice the square root of the variance of the inner product between the derivative of f and u. So this is the inner product of the derivative of f and u. So if you have an f and you are able to express f as a delta of u, then you can estimate the total variation distance by this variance. Let me give a proof of this theorem, because the proof is very short, and it more or less it relies on all the things that we have done so far. So here is the proof. So remember, to estimate the total variation distance, you have to estimate these quantities, where phi is a function that satisfies these two conditions. So you take a C1 function that satisfies this condition and this condition. So it's bounded by the square root of pi over 2, and the derivative is bounded by 2, and you want to estimate this quantity. Because remember that this is exactly what appears here. You have to estimate this. Okay, so now what we're going to do first to compute this part, to compute the expectation of f times phi of f. Now, first of all, f is delta of u. Okay, we assume that f is delta of u. So I can replace f by delta of u. Now I have expectation of delta of u times phi of f. I can use that f, delta is the adjoint of the derivative. So now I use that delta is the adjoint. So this quantity can be written as the expectation of u inner product in h with the derivative of phi of f. This is just the fact that delta is the adjoint of the derivative. This is the duality relation formula. Now I use chain rule. The derivative of phi of f is phi prime of f times d of f. And phi prime of f is a scalar, so it goes out of the inner product. So conclusion, the expectation of f phi of f is equal to this. So now I plug this here, and I factor phi prime of f. So I get phi prime of f factor of 1 minus df inner product with u. Okay. Now phi prime of f, remember, is bounded by 2. So I put absolute value inside, I bound phi prime of f by 2. And then here is another important fact, is that the expectation of df inner product with u is 1, because the expectation of df inner product with u, by the duality formula, this is f times delta of u. Okay, but delta of u is f. So this is the expectation of f squared, which is 1. Okay, so the expectation of this is 1. So this is, now I can use Cauchy's vars, and because the expectation of this is 1, this is less than twice the square root of the variance of this quantity. So I think that what we have used is just estimate this by this, and now there is no phi here. So now you take a supremum with respect to all the phi's that satisfy this, and you get this total variation distance bounded by this quantity. So it's a very simple proof using just Malliavin calculus. The important thing is that f is normalized and f is the divergence, and this has been used here and also here. Okay. So in other words, now, if you want to estimate this total variation distance, you have to estimate this quantity. So that's the main idea. So this was done in, I think, 2008, more or less, by Nualart and Piccati. And since then, there has been an explosion of papers where people have tried to apply this theorem. Actually, the theorem, if you look at Nualart and Piccati theorem paper, you will not find this formulation. They use another formulation, more complicated, using the operator L-1. It's a little bit different, using chaos expansion. So it's not exactly this. This was discovered later, but essentially the ideas were already in the paper by Nualart and Piccati. So this,
excuse me, Professor, one question.
Sure.
So in this inequality, we have on the left-hand side the variable set.
Yes.
And how is it connected with the right-hand side.
No, there is no, Z is a fixed random variable, which is normal 0, 1. So there is no Z here. So this goes.
Independent of set.
Yeah, because Z is a random variable fixed. This is in distribution. This variation depends only on the distribution of Z. Okay. So actually this goes back to this theorem here. There is also no Z here.
Ah, yes.
But if Z is 0, normal 0, 1, you get this. There is no Z here.
No.
And this is because this depends only on the distribution of Z. So the fact that Z is Gaussian, of course, is used to prove this. The Gaussianity of Z is important. But the Z itself as a variable plays no role because this is a quantity that depends only on the law of Z, not on Z itself.
Okay, thank you.
Okay, very good. So now let's continue. So now let's go to our result. So remember, what we want to prove is this. So the F is now this. This is the spatial average. Remember, this S and T is 1 over n power t integral on 0 n power d of u to x minus 1 dx, where use the solution of the stochastic heat equation. Okay, so this is the spatial average. Normalize it, divide by the square root of the variance. And Z is a normal 0, 1 random variable, and you want to prove this. So remember, the first thing you have to do is to write F as a delta of U. So that's the first thing. How do you write F as a delta of U? F has variance 1, and this is in our context because, because F is this, yes, variance 1. And it has expectation 0 because U is centered. But how do you write this as a delta of U? Well, don't be confused with the U in this theorem, the U in the previous theorem. This U here has nothing to do with the stochastic heat equation. Okay, the U here is a U which appears in the representation of F. Okay. So the idea is as follows. So you use the mild formulation and UTX minus 1. Remember, this is the stochastic integral of sigma of USY times the heat kernel W ds dy. And there is a dx missing here. Should be a dx here, which is missing. Okay. And now here you can use the Fubini theorem, and you can first integrate in x, and the only thing that depends on x is the heat kernel. So you first integrate the heat kernel in x in 0 n power d, then you multiply it by sigma, and then you get a stochastic integral. So this is just Fubini theorem, and there is a dx missing here. So now I have S and T written as a stochastic integral of an adapted process. But you know that the stochastic integral is a particular case of a delta. So in that way, you have a representation of your random variable as a delta. It will be a delta of all of this. Okay, because the stochastic integral is a particular case of a divergence. So now the idea now is that you define, so you prove, you get that this S and T is a delta of V and T. And what is V and T? V and T is this quantity, here it is, with the factor 1 over n power n t, 1 over n power d. So 1 over n power d times sigma of USY times this deterministic quantity. So this is an adapted process because U is adapted and it's square integrable, and S is delta of V. So now I have represented S as a delta using the fact that stochastic integral is a divergence, and now we are in a position to apply the theorem. So we are in the position now to apply this theorem, and for this you have to compute this quantity where the U here, of course, is going to be the V. This is going to be the U now. Okay, so now I have to compute the derivative of this and project this. And I will not give you many details, just one page of computations, that's all. So you have to compute, this is what you have to compute. You have to compute the variance of the derivative of S projected on V. The derivative of S is the derivative of delta. Now we use here the commutation relation between D and delta. This is the identity plus delta of V. And then you project this into V. So you take the inner product of this with V. And then you get the normal V square first. You get this times this. And then you get this times this. And using Fubini theorem, you write something like this. And finally, the variance of this quantity, this is what you want to obtain, is less than twice this variance, plus, and the variance of this is stochastic integral, can be obtained using the isometry property, which is here. So that's the quantity you want to estimate. So the total variation distance will be bounded by the square root of this. So now you have to estimate all of this. How do you estimate this? Well, to estimate variances and covariances, you have Poincare inequality. So the main tool to estimate these quantities now, and I'm not going to do this, of course, because it's very technical, is to use Poincare inequalities. And then remember that when you use Poincare inequalities, you get Malliavin derivatives. So at some point, you're going to get a Malliavin derivative of U. So now a basic ingredient is an estimate of the Malliavin derivative of the solution. And this is a fundamental result to estimate, to our estimates. And this is the fact that if you take a solution U of the heat equation and you take the Malliavin derivative, this is bounded by the heat kernel, Pt minus S of x minus y times a constant. So that's and this is true for every P. So the constant, of course, depends on everything. And that's, I will not give you the proof of this, but maybe I should give you some intuition or ways that are true. Here it is. So the derivative of U is a solution of a linear SPD, because when you take the derivative, you use a solution of the Mail equation. So when you apply the derivative to the Mail equation, you get something like this. And then what happens is that this is a linear equation, so this derivative appears here. So now you can use Picard iteration, and then the LP norm of this will be essentially bounded by the initial condition. So usually when you have a linear equation, you can bound the solution by just the initial condition. And then the initial condition sigma has moments of all orders, and this is where the heat kernel appears. So of course, all of this is very, I am just waving my hands. I'm not giving you details, but this is the main idea. So once you have this bound on the LP norm of the Malliavin derivative by the heat kernel, then you can use Poincare inequality and you can estimate this. And in that way, you complete the proof of this estimate here without entering into too many details, okay? So that's a proof of this result. And now I would like to give a couple of extensions, maybe. I still have some time.
Yes.
How much? Okay.
It's 12:20, 10 minutes more or less.
10 minutes, okay, that's enough. So I will just talk about a couple of extensions of this. Of course, there have been extensions to other equations like the wave equation, but I'm not going to talk about this. With some collaborators, we have proved similar results for stochastic wave equations and also for fractional heat equations. They have been proved. But there are a couple of extensions for the stochastic heat equation that we'd like to mention. The first one is when instead of taking the average of U, you take an average of a function of U, G of U. And the motivation for this is that you know that when sigma of U is U, so the equation is linear, and you have the space-time white noise, then when you take the logarithm of the solution, so the solution is not negative in that case, and you take the logarithm is the solution of the KPZ equation. And this is a topic that many people are interested in, this, which is a ill-posed equation. And I'm not going to tell you what is this, but essentially just tell you that the logarithm of U, when sigma of U is U, and you have a space-time white noise, dimension 1, this is the solution of the Hopeful equation, and then you would like to have also the central limit theorem when you have the logarithm. So for this, we have developed an extension when you have a function of U, G, which here in particular is the logarithm. And it turns out that in that case, with a rate 1/n, you have convergence to the normal distribution. And the variance can be also computed explicitly. And you have also these quantitative, you have total variation estimates, which are of the form n to the power minus 1/2 also. Okay, so you have the central limit theorem for this solution of this KPZ equation. Okay, this is the result that we have obtained. But I would like to tell you that in order to obtain total variation estimates, we have been able to obtain total variation estimates only if sigma of u is equal to u. Because if sigma of u is not equal to u, the method I explained before requires a second Malliavin derivative, requires an estimate of the second Malliavin derivative. And this, when sigma of u is not equal to u, this is an open problem. And some progress, I have made some progress on this estimate, but then the estimate is not of this form. And I have obtained it, so this estimate is for sigma of u equals to u. And this is when S1 is less than S2 and is less than T. I have two Malliavin derivatives, and I have a product of two heat kernels, PT minus S2, P S2 minus S1. And this time of estimate, when sigma of u is not u, we cannot expect to have something like this. And there are estimates that we have obtained recently, but they are more involved than this. And we don't know still if these estimates allow us to get total variation estimates for this situation. What is true is the function of central limit theorem. This is true. But total variation estimates are obtained only when sigma of u is equal to u. So that's one remark I'd like to make in connection with the KPZ equation. Then my second remark is about the initial condition. The initial condition is 1. So if the initial condition is not 1, you cannot expect in general to have these results. Well, you can take some initial condition that goes to 1 at infinity or something like this, but if you take an initial condition that it's, for example, integrable or something like this, you cannot get these type of results. But there is another situation where you can get a central limit theorem is when the initial condition is a Dirac function. Okay, and sigma of u is u. So we are in dimension 1. So this is 1 here, and this is the equation. Okay, this should be w. Okay, and then instead of a 1 here, you have pt of x because the initial condition is a Dirac function. Then in that case, what happens is that if you take ut of x and you divide by pt of x, so again, this is related to the KPZ equation. What happens is that in that case, this is stationary in x. And the stationarity was proved by, in a very interesting paper by Amir, Corwin, and Questel devoted to KPZ equation, devoted to asymptotics of the distribution of the KPZ equation. And they proved that this is stationary in that case. So I repeat, the situation here is completely different. So the initial condition is not 1, it's a delta function. U is not stationary in space at all, but u divided by pt of x is stationary. And this is a kind of surprising result. And again, it's ergodic, provided that, well, it's ergodic because here, it's ergodic provided you have this situation. But actually the stationarity is 2 in RT. So you can take RD here because this is general. I am not taking here the space-time white noise. Well, exactly. The stationarity was proved by these authors in the case of a space-time white noise, but we proved stationarity of this ratio in general, okay? And ergodicity provided that this is true, okay? And then you can say, well, you have the situation where the initial condition is a Dirac function, sigma of u is u, and then you have stationarity. Can you prove an ergodic, can you prove a central limit theorem? And then the answer is yes. And here it is, but the situation now it's a little bit different because first of all, there is a logarithmic factor in the normalization of the averages. And also in the total variation distance, again, a logarithmic factor of n appears instead of 1 over square root of n. And this is the case of delta 0 and delta equals to 1, okay? So there is a logarithmic factor, and this logarithmic factor appears due to this singularity of the initial condition and singularity of the heat kernel at 0. So that's something which is interesting. And this is in dimension 1 for a space-time white noise, and in dimension t, dimension 2, dimension d bigger or equal than 2, there are results, but then depends on this quantity to be finite. And then this is the type of results that we have obtained as n goes to infinity. And here there is no logarithmic factor in that situation. Okay. Provided this quantity is finite. This plays the role of the measure being finite in the case where the initial condition was 1. Okay. And finally, so this is the case where this is finite. And then in the case of the risk kernel, then you have again a logarithmic factor with beta is 1. And then if not, you get a kind of a phase transition in the case beta equals to 1. Okay. So it's an interesting phase transition. So this is much more complicated than the previous results. And I will not, but the techniques are the same. You estimate this total variation distance using this Norden-Pecati method, but then the computations are much more involved. Okay. And then just to finish, this is the list of references. So the first paper that was done in this situation with my correlation with Hingyu and Vitasari. Actually, Hingyu was a former student of mine, and he was the one that suggested this problem 3 years ago. And this was our first result with Lauri. And then we studied the case of coloric noise. And then I've done several papers with Davar, Koshnevisar, Lechen, and Vipu. And the case of delta initial condition is this one. Okay. And these are submitted papers already. So these are some of the papers that have been published in this topic. And there are other situations that have been considered, the case of the wave equation, as I told you before, case of fractional equations, but I'm not going to talk. So I just wanted to give you some general ideas of the methodology and the results that are obtained for these spatial averages, which is a topic that I have been developing intensively in the last 2 or 3 years. And I think that I'm going to stop here. Thank you very much for your attention.
Thank you very much, Professor David Nualart. So we have time for questions. Is anyone willing to ask something or give any comments? Please feel free to unmute your microphone and ask. Maybe before someone asks, yes?
No, Carlos, it's a question. The people is able to deactivate the microphone?
By their own, yes, they can.
Oh, yes? Okay.
Yes, they can. So before someone asks, I have one general question. What we notice is that the Malliavin calculus is kind of the right tool to study certain stochastic differential equations, like the stochastic heat equation. And but I'm not sure, maybe Professor Malliavin was not thinking at the beginning about stochastic partial equations. So I mean, my question is like, the Malliavin calculus is the right tool for these models, but in general, which other fields or topics or models we can work with this calculus?
Well, originally, the Malliavin calculus was used by Paul Malliavin to prove this Hormander theorem. And then in probabilistic terms, this was to prove that the solution of a diffusion equation, which is a random variable, has a density, which is smooth. So essentially, the Malliavin calculus has been used a lot to prove that given a random variable, which is a function of a Gaussian process, which is a solution of an equation, any type of equation, diffusion, stochastic partial differential equation, whatever. So Malliavin calculus is a method to prove that a given random variable has a density and the density is smooth. So this has been the main application, and which developed from the Hormander's proof of Malliavin. But the application I am presenting here is a little bit different, because this is an application to estimate total variation distances, combining Malliavin calculus with the Stein's method. And this is new. This has been developed very recently, in the last 10 years only. And this was not included in the first applications of Malliavin calculus. Malliavin calculus was applied to estimate and prove regularity of densities. This was the main application of Malliavin calculus, estimation of densities. Now here we are doing something completely different, is to estimate the total variation distance between a random variable and a normal 0-1 random variable using Stein's method combined with Malliavin calculus. And this Poincare inequalities also to estimate variances. So that's another application of Malliavin calculus, which is different from the original ideas of were developed from Malliavin.
Right. Okay. Thank you very much. Questions? Another question or comment?
Well, I have one, but maybe it's
go on, Hector.
Yes. The only question is there any you were working with a Brownian motion depending on t and x, no? The state and time. Is there any motivation to study this kind of a process?
Yeah, the study of SPDs perturbed, so stochastic partial differential equations perturbed by noises appears in physics, in finance, in many areas, because you have you have uncertainty and you have measurement errors, and even these type of equations appear in physical models. So the study, like for example, growth models for polymers, these KPC equations also. So these equations perturbed by noises, partial differential equations perturbed by noises appears in many branches, and usually people assume that the noise depends on time and space, not only on time. Like for example, when you have this growth of interfaces, the noise depends on the position and on time. And the usual assumption is that it's a space-time white noise. This is the basic assumption. And the more general assumptions is that there is some colored noise in a space, okay? But these are models in many areas of engineering and physics, and people have been applying these models for a long time.
Okay, thank you very much, Professor.
Actually, like since you were talking about the ergodicity of this model and you were relating it to the KPC equation, so I suppose people notice something. What I mean is that people observe something in the nature that is related to the ergodicity proved in your theorems.
Yeah.
Do you see what I mean? Like people observe something in the nature, in some physical phenomena, and that is related to the ergodicity of the solution of the equation.
Yeah, they observe stationarity, and usually in this context, when you have stationarity in many situations, you have ergodicity immediately also. If you have enough noise, I mean, you have enough noise to have ergodicity.
Yes. By the way, I have these notes. Do you recognize?
Yes. This was
these notes is a mini course.
Mini course in Utah. This was organized by Davar Koshnevisan long time ago. And this is a good reference. There are lectures by Davar Koshnevisan, by Robert Dalang on the wave equation. And I have a paper on applying Malliavin calculus to the equation. And there is also notes by Karl Muller and someone else, I think. I don't remember.
Yeah, people make lots of reference to this book.
Yeah.
Mm-hmm.
Yes. More questions, more comments?
No.
Should stop sharing the screen.
Okay, well, thank you very much. Everyone can unmute your microphone and give a big applause to Professor Nualart. Thank you, Professor. Thank you very much. Okay, so terminamos el día de hoy. We have finished for today, but tomorrow we resume for this celebration of the 60th anniversary of the department. At the same time, the first talk is going to be at 10 o'clock.
At 10 o'clock by Professor Anton Wacol-Binger, which is here. Actually, I can see.
Oh, great. Okay, and the
well,
second one is at past 11, right? Half past 11?
11:30.
11:30, yes.
By Victor Perez.
Victor, yes.
And okay, so I hope you can stay with us for tomorrow. And thank you very much for.
Thank you, everyone.
For our speakers, and to general to all the audience.
Yes, so I'm going to finish, Hector, with this map. So here we can see that actually our speakers are kind of neighbors, right? So